Okay, all right, guys, welcome back to the second half of the class. And I think I forgot to mention why in the standardization, I specifically tell you that I chose X-train right here, fit X-train. I forgot to mention. So one thing that you can think when deciding which data to go into which is that think about this. Training data is something that you have, right? But treat test data as the data that come from the future. Okay, and that will clear things up, right? So let's say I want to scale my data and I want to fit it to the standard scaler. I cannot use the future data because that's something that I technically don't have. I mean, I do have it, right? But imagine that you don't have it. So if you don't have it, you cannot put it in here. So if you were to put X test in here, it's wrong because you are using the future data. So that's why. Right? This doesn't work in I guess in that sense. Okay. And what about this? If I only put X, you think that works? I mean, it won't give you error, but do you think this is correct? Well, X has 100 rows, right? X train has 70 rows, and X test has 30 rows. Okay. What do you think? Is X okay or no? It's not okay, but you know why? Yeah, it contains the test data, which is from the future. So you cannot use this one. So to be completely consistent with the way that we do like unbiased in statistics, you have to use the current, the one that you have, which is just X-train. Okay. Okay, that one. So keep that in mind. Okay, and it will clear things up in the future. Okay. I guess we're done with the standard scaler, right? So finally, we can start talking about the machine learning algorithm. Let's do it, okay? So the first algorithm that we're going to do is called Perceptron, okay? So Perceptron is, I guess it's a name after something called neuron. Like it's something named after neuron. And neuron is a biological cell in our body. And as you can see that you might have heard something called artificial neural network, right? And it's the mathematical model that has the same, that's inspired by the architecture of your biological neuron cell, right? But nowadays, people don't make that distinctions, that connections anymore. So when you think about perceptron nowadays, just think it's just a linear function. That's all it's doing, a linear function, okay? And this linear function or linear model, what it's doing is actually, it's going to give you the binary output, okay? Which is going to be class -1 or class -1 or 0, okay? So think about linear function that give you either 1 or 0. That's what it's doing, okay? Although, I mean, it does have some historical connection with the neuron because of the earlier research in the past, okay? Okay, and I do put in some, you know, like this connection between the biological cells, but you can just ignore that nowadays. People don't make that connection anymore. But I want you to focus about this, okay? So the input to the model or the function is the x, right? And as you can, and we talked about x as being consists of vector. So this is the columns. In our case, we only have 2x, which is the petal width and petal length, okay? And what it's doing inside is that once the input goes into the model, it goes into this function right here. So this function is essentially a linear function, right? Because you have, this is a constant. This is the constant too. It's called the weight, okay? But this is not the scalar value though. This is not just one value. This is the vector value. So you do have multiple scalar weights, okay? But it's a constant nonetheless, okay? And this is your input right here, x. So if I were to expand that, so this one is more like a vector notation. If I were to expand that into a more scalar notation, I would get something like this. A constant times one constant times x1, another constant times x2, and so on, okay? And if you collect all the w and put into a vector, we call it the weight vector right here, okay? And if you put all the W0 right here into a vector, it's called the, I guess not even it's a scalar value, so then intercept. Okay. So when I say constants, another way that we usually talk about it, it's called parameter. This guy right here. So when I call the model parameters, think about it as a constant that is used internally in the model, in the equation, for example, in a linear equation like this. Okay, so these are model parameter. Okay. All right. So internally, you can the model is gonna calculate the value called the z value. It's called the net input, but you just ignore what it's called. It's okay, right? And another thing that it's gonna do, it's actually gonna do something called activation function. Okay. Activation function is another function that you can specify. I guess now for this perceptron model, it's actually not even a function. It's just the one-to-one mapping. This function is saying that if you put any input into it, just output the same value. So this is not even a function. It's just one-to-one mapping, right? Just whatever input, give it the output. Okay. But the reason that I introduce this right now is that later on, you will be doing the neural network. And the neural network is actually built on this same building blocks, but the activation function is actually something that is nonlinear. And that's going to give you a lot more power in your prediction due to this exact thing, activation function. But for now, this is not even a function. It's just one-to-one mapping. That's it. And then the output of the model, as I tell you, is either 1 or 0 or 1 or negative 1. It's determined from this statement right here. So if the z value or the output from the activation function is larger than 0, it's going to output you 1. If it's less than 0, it's going to output negative 1 or 0. Okay? So it's a pretty, I guess, straightforward equation. It's just a linear function. But it does have some condition into specifying the class, right? It's either 1 or 0 or 1 or negative 1. So that's how the model gives you the class label, per se. Okay? And I'm going to modify things a little bit. So this one is just so that I can write things in a shorter manner. So I'm going to say that the feature is the same, right? But the input is actually going to include number 1s in here. So it's going to be x0. So x0 is just the dummy value. So that when I write my z function, which is something like this, I can just get rid of this guy right here and just write something like this. Okay, so this is for shorter notation, and that's it. So if you don't, don't worry about it if it doesn't clear, it's not clear to you. It's just so that I can write the same thing, but I can just write z equal to x dot w. That's all. That's all I'm doing. Okay. Right. So once you do this, then this is the model parameter, right? So now we know that in the perceptron, we need to have the model parameter. And actually another type of model parameter, apart from the weight, which is a constant. There's another parameter that is the, I guess, connected to the process of learning itself. Okay. So the learning itself, the process is actually to find the weights and intercept. Okay. So actually, your job is actually to find whatever this is and this that fits your data the best. Okay, so that's the process of learning. Learning is to come up with the best value of this. Okay, and in the process of learning, there's actually it's kind of like it's an iterative process. For example, if I were to do this, okay, this is your input. Okay, you input the data into it, right, and then it goes into this linear function. It goes into the activation function. And normally, if you just want to predict something, it goes into this condition right here, and it's done. Okay, so that's the prediction part. But for the learning part, it's actually looping the result back into here, into what's it called, the weight update. Okay, and when you do this weights update, there's also another parameter that is quite important. It's called learning rate. Okay, L-E-A-R-N. Learning rate. Okay, and we'll talk about it later. But I just want you to know that when you talk about the model parameter, there's a parameter that are inherent to this equation down here. So that's like a parameter for the model, for the equation. But then there are also parameters that are related to how the model learns. And for this Perceptron, what we're going to use is called learning rate. Okay? So you need this information because when we are going to build the model, you need to specify what is the learning rate, what is the weight, or actually not the weight, but what are things that you need to do. Okay? All right, so let's go back into our code and we're actually starting constructing our model. Okay? In order to do that, I'm going to resort to another class blueprint called Perceptron. So this one is loading from the scikit-learn and linear model. The Perceptron is a linear model. Okay, let's do that. Okay, so whenever you see the capital letter, that means that you gotta create the class instance out of it. Okay, so let's do just that. Okay, the easiest way to do is go Perceptron, like that. And there you go, you're done. I mean, this is too short, okay? But it's actually working. If I were to type this and I press enter, this is the class instance from the class Perceptron, okay? But this one seems awfully too short, right? Let me just show you one thing real quick. So I'm gonna keep this into ppn and do that, right? And let me just draw it out to see what it is, okay? As you can see that this one is a class instance. It contains a lot of things, actually a lot of things. If I scroll down to it, then you can see that there are many things in here, including the weights and the intercept and the learning rate. See the learning rate in here? See the, I guess the W's in here? The intercept is right here, fit intercept. And I think the weights is called the class weight. See, so right away, when you create this class instance, it's actually contain, like a lot of all the parameter, and then a lot of method that come with it. But it's just awfully too short. And what are these value, right? I want you to take a note at the document one more time. So sklearn, I'm going to search for Perceptron this time. Okay. Okay. It doesn't always go to the stable version. Okay. So the Perceptron is a class again, right? And in this class, if you don't do anything, you just do the parentheses, then this is what it's doing actually. This guy right here. It's doing all of this, which is this argument. So that means that you are setting these parameter to be the default value. For example, you set alpha to be 0.001. You set L1 ratio to be 0.15. You set fit intercept to be true. So actually that's not the W0. It's actually class weight. Also, actually not even class weight. Go down below, you'll see. Okay. But these are the parameters that you use to set your model. Okay. But this might not be the one that we want. So I'm gonna customize my model a little bit by using some of the things that I show in your slides in your code. For example, this one is a learning rate. Eta 0 is learning rate, the one that I just talked about. This guy right here. So I want to change this one to be something else. I want a slower learning rate. So I can do this. Okay, I can do eta 0 equal 0.01. Okay, and that's gonna make the new class instance with this parameter setting. Okay, I want something else. As you can see that I want random state, and you can guess like if you specify the random state, that means that your model is gonna train in a similar way, and I think that's something that I want. So I want it to be 1. Okay. And I want, there's something called n, iter no change. So any of this, if you're wondering what this does, you can always go back to documentation and search for it, like n, iter, no change. So the default value is 5, but if you want to see what it does, just kind of search down, see? It's the number of iteration with no improvement to wait before early stopping. If that doesn't make sense, just stop it right now. But take my word for it. I'm going to set into 10. Okay. So I'm going to do verbose. Okay, verbose is splitting out a lot of information. So if you see, go back to your here, you can see verbose. Okay, the default one is equal to 0, but okay, I guess the explanation is not that detailed. Verbosity level. So verbose means that output a lot of things. So if you set it to be 1, then it starts to output more information. Okay. All right. So with this, I can just, I guess, I can just run this. Okay. I guess in my code, it's a little different, right? Because I do have another block on top, which is something like this. And sometimes I do this, sometimes I don't. It depends on kind of like how you structure your code. But I'll just show you again. I can do this too. Wait, where is it? It has to be, oh, not here. Oh, shit, below. Way below, right? Yeah, way below. Right here. So in certain cases, I like to kind of specify the parameter of the model right here. And then when I type it in here, I just have to replace it like this. So this one might seem a little bit weird, right? Because it's the same, it's repeating, but it's not. Like if I were to change it to be 00000, right, eta 00, then I gotta change this one too. So this one is here, but the first part is the actual argument name. Okay, so this one you cannot change because this one is from the library, but you feel free to change the latter one, which I mean for no specific reason, I like to keep it the same. So I just have to write eta 0 like that. Okay, just to make sure that you don't get confused why it's the same name, because I just chose it that way. Okay, so random state, go to random state, and end eternal change, go to that, something like that. So it looks a bit long, but the nice thing is that you know where to change. You change it from here, and it changes it down here. So sometimes you can see that this one it can get quite long, and when you put it up here, then you kind of know what it does, right? Because it's quite obvious. Change here. Right? So that's my style. I like to keep things on top, the things that I want to change on top, and I don't want to mess with this later on. It's too long, that's all. Okay? All right, so you have constructed your model, right? Let's go to the process of actually learning it. So now you haven't learned anything, now you're learning it, okay? So the learning part you can do very easily with the command ppn. Right? So that's the class instance dot fit. Okay? So fitting, it's like learning to finding the best parameter, weight, and intercept in your model. And again, you have the choice. You have to give it x and y. Okay? The wrong way to do is to do this, x and y. Can you guess why this is wrong?อันนี้ผิดยังไงครับ ถ้าทำแบบนี้ fit x and y how is this wrong? It's the future data again, right? Remember, this x and y is a whole data. You're fitting your future data. No, it doesn't work that way, right? Because you're treating your test data as your future. So you gotta put your x train, right, and y train. Because this is the only thing that pretend that you only have this data and you won't make mistakes. Okay? Okay. All right. So why don't we just enter? And congratulations if this is the first time you do AI. Yeah. Congratulations. Okay, you just finished just finishing your AI training. I don't know if that's your first AI training, but yeah. That is exciting, right? Yeah. Okay, it's done. Okay, but you know it's splitting a lot of information for you. So let's just try to understand what it's doing. Okay, let me go back here.
So I just feed the machine with
Yeah, you just feed the model the learning data, the training data. So it starts learning from your data. That's machine learning.
What is it if I give ChatGPT some input, like some
No, when you give ChatGPT the text data, you give them, that's called the prediction tasks. That's not the learning tasks. So let me go back here. Actually, with ChatGPT, it's actually the same process. Like the company behind it actually have to do 1, 2, 3, 4, 5, 6, probably, but much more complicated than this, right? When we're feeding the text into ChatGPT, we're actually doing number 9. We only do step 9. But you remember, like, have you ever heard like that when they make that ChatGPT model, they have to use like billion of, like you have to use a lot of energy. Like you have to train them using like the GPU, and it costs, I don't know, like $1 million or something. That's the part where they have to do number 7. So ChatGPT, when you do number 7, it costs a lot of money because they have to use like really specialized hardware, and it takes a lot of electricity. But then once 7 is done, you just have to do number 9 to get what you want. So right now we're doing number 7. So we are building the model. Okay.
So it's taking so much energy.
Well, this one, the laptop. Yeah. I mean, this is a linear model. So this is the best. So let me show you this one. In your model, right? The only thing that you need to find is I guess 4 things, right? 2 things. You need to find W1. Okay, let me show you this. Okay, so the only thing that you have to find in your model is W1, W2, and W0. So you have 3 parameters to work with. I remember like ChatGPT, they have like 1 billion parameters to work with. So do you see the difference? Like when you're training the model, when you have to optimize for 3 things, 1, 2, 3, it's very fast. That's why it's done on your laptop. But in the actual ChatGPT model, they have billion parameters. So think about this, but billion values. Then that's why it takes so long and takes a lot of energy.
And like employee feeding them with this billion parameters?
Yeah, in ChatGPT model, the building block is still the same thing. It's still Perceptron, but it's architected into something called like a neural network. It's called like a deep neural network. It's called transformer. And inside, in each of the Perceptron, yes, there are only 3 things you gotta worry about. But they have, I don't know, like 1 million perceptron in their architecture. And each one, they need all of this to be optimized. So that's why it takes so long and takes so much energy. But you only have 1 perceptron. So you have to optimize 3 parameters. That's why it's done so fast, right? Okay, so, but I want you to understand what is happening in terms of the output, okay? All right, so let's just skip into here, okay? So in here, you're gonna see something called epoch, right? I think it's pronounced epoch, right? And in my code, I think I have something around 12 epochs, okay? Let me know if it doesn't pronounce epoch, right? I think it's epoch, okay? The epoch is, it's a number that counts how many times the model reads your data. So what it's doing is that it's gonna get, so right now you give them 70 observation, right? Your X-train has 70 rows. You give them 70 observation, it's gonna go through 70 sample and optimize the parameter 1 time. So after 70 data, 70 row, it changed the weight 1 time. That's 1 epoch. But then if that is not enough, it's going to go through the 70 sample again and optimize and change the value of your weight 1 more time. That's the 2nd epoch. And the 3rd epoch is they're going to go through the 70 rows again and change the weight 1 more time. So that means that in my model, during my training, the model is actually changing the weight. It's trying the different weights 12 times, basically. It's optimizing 12 times, and it's done. Okay, so that's what it means by epochs. Okay, in detail, that's slightly different from what I told you, but the general idea is something like this. Okay, so you want to make sure that the epoch is not too long, because if it's go to like 10 million, then your model is never going to stop. Okay, and each time that it's doing this, you should take a note at something called loss. So loss is something that the model keeps tracks in order to say that if it's done or not. For example, if the loss is high, that means that the model is still not fitting correctly to the data that you've given. And as you can see that the first time, right? The first time the model is actually choosing the weight randomly. So that's why the loss is high, because it never reads anything, right? But once it's training itself one time, one epoch, you can see that the loss decreases, okay? And from now on, actually this one, there's still non-zero loss, but then it's, the decimal place is too much, so that's why it's 0, okay? But you can imagine that after each epoch, the loss is decreasing. And at some point, we're going to have to tell the model to stop, right? And that is exactly what this parameter is doing. N iter no change. If each epoch doesn't give you better results 10 times, just stop the model. So I can show you something that might make more sense. If I were to reduce this N iter no change into maybe 3, you can see the difference. I can rerun it again. And you're going to see that it's actually run only 5 epochs and it's done. Because I think it's going to, like after epoch number 3, I don't think there's any improvement. And it's going to run for 3 more times before it decided to stop early. So that's what this N iter no change is. So usually this one is useful because if you run a more complex model, you might want to adjust this so that your code doesn't run forever. That's my suggestion. So this one, I keep it just, I experiment to see if it's, sometimes if it's not good, then I increase this number so that it run more. But if it's too long, I reduce this number. That's the thing that I use. Okay? And that's it. And then the rest is, so bias is actually the W0. And I think NZ is number of weights. So you have 2 weights and 1 bias. So as I tell you, W1, W2, and W0. So this is just telling you the kind of like the actual value that it's using. And T is called the number of row reads. So the first time it reads 70 rows, right? The second time it reads total of 140 rows because it goes through the second time. And as you can see that by the time that my model finished training, it has read the data into it, 350 data. So 70 data, read it in 5 times. The total amount of calculation is 350. So that kind of gives you the overall idea of how much computations the model used during your training. Okay. All right. So that's the explanation of what it is. Okay. And once your model is done, I think you should be able to. Again, there's also another concept for convergence. So whenever your loss start to stay the same, that means your model is converged. So that's why it's called convergence. Or the other way of saying is that your weight doesn't change anymore, then the model should stop doing. Okay. And I just want to let you know that it depending on your data also. If your data can be splitted by the linear line like this, it's called linearly separable. But then if your data cannot be separated by a linear line, it's called not linearly separable. Okay? So there are two types of data for the linear model. So this type of data, if you have this type, your model will converge, meaning that after a while, your epoch will give you no improvement, okay? But then if you do this, if your data is like this, then it will never converge because it's going to keep finding the right way, and it can never find the right line to separate your data perfectly. So it's going to keep kind of like switching between different orientation, and it never converge. Okay, so in that case, you're going to have to be a little bit more careful in determining your model parameter so that it knows that now it should stop after some time, okay? That's kind of the detail. If we encounter this behavior, then we'll talk about it later, okay? But just want to let you know that there might be a case in the future that your model is not converging, like it just keeps running forever, and you gotta have to stop it, and then just think about your parameter setting a bit more in order to make it stop, okay? All right, so let's evaluate the model, right? Because the model is already fit, so we should be able to validate its performance, right? And the one that we're using is called accuracy, okay? So accuracy is the number of the class that are that it gets correctly, okay? If the accuracy is 1, that means that your model is perfect, I guess, from our evaluation. Okay, it doesn't guarantee it's perfect in the real production run, right? But during our testing, if it's 1, then that means that at least, you know, it's a pretty good model, right? If it's like 0.2, that means that it can only predict the right value 20% of the time. If it's 1, then it predicts the right value 100% of the time. So you're looking for something that's close to 1 when you calculate accuracy, okay? And the way that we do that is actually we're using the test data set, okay? So this is quite important. When you evaluate your model, you want to use something that the model has never seen before. As you recall, we only supply X train to the model during fitting. So the model doesn't know about the test data set. That's why when you choose the test data set for evaluation of your model performance, it's a good metric to get the estimation of how the model will perform in production. Okay? But keep in mind that right now, even if you choose the test data set, it's actually a little bit biased. Okay? It's not terrible, but it's not the best way to evaluate your model because you haven't used the validation data yet. All right, so let's do the model performance evaluation. Okay, so in order to do that, I'm gonna use another. I guess I'm gonna use another function called accuracy score from from scikit-learn. Okay, I can do that too. Oh, actually, before I even do that, I need to use my test data to perform the prediction. Okay, so my model is done, right? So I'm going to use the test data to determine the accuracy. So first thing, I want to, oh, I forgot to show you this one, sorry. The model actually contains the coefficient, so the ppn, right, dot coef underscore. So that is W1 and W2 that I was talking about, the one that get optimized. And then there's also ppn.intercept underscore, so that is the value of W0. So as I was telling you, right, we only optimize for 3 things, and these are the results from the training. Okay. All right, so in order to evaluate model, we got to use the test data. So we can do ppn.predict. Okay. In this part, this is not number 9 yet. This is number 8 in our process, right? Okay, we are evaluating a model. Even though we are predicting the test data. Okay, so we do x test std. Oh, hold on. I think I made mistakes. Yeah, I made mistakes. I have to use the standardized data. See, even I do make mistakes here, right? So if I use this one, the model can train, but it's actually giving more weights to I think one attribute that has higher value. So I gotta use std. So be careful with this. It's easy to make mistakes. Okay. So I'm gonna go here. I'm gonna use test x test std also. Remember that we also standardize our test data, right? So we have to use that because the model is actually expecting the standardized data. It does not expect the raw value. So you gotta give it the right way. Okay, this one? Yes. Okay, this one is W1, this one is W2, and where is it? It's actually here. If I go to my model, this guy. It's W1, W2, so that's the coefficient, and the intercept is W0.
But I get different values to you.
Because I only optimize, okay. That's a good question. So I should keep this value the same as you do. You have 10, right? Okay, let's run again. Yeah, yes, it's good. Let's test it to see if that's the case. Do we got the same value now? Yes, okay. Yeah, that's why. So a lot of things can go, can make the result change. Okay, now I'm going to predict my test data. And this is okay, right? Because now think about this, like when we want to evaluate our model, we should have the data from the future now. Let's say we collect more data, we want to test the model, so we can use this data, okay? And these are the results from the model. So this is 1 and 0, so the two class, right? I'm going to put this in my y predict, okay, like that. Yeah. So let me show you, this is my y predict, right? And this is my y test, okay? As you can see that the one on the top is the value of the class that the model predicts from my test data, right? But because it's my test data, so I know the answer. My answer is y test. This is from our observation. And the accuracy is determined from comparing these two to see if the model predicts the wrong answer or not. If the model gets everything right, completely right, then your accuracy go to 1 or 100%, right? And if it's not 1, that means that there are some misclassification occurring between y predict and y test. Okay, and the way to do that, you can also do that with Python natively. It's okay, but if we already have a function called accuracy score, I think I kind of skip things a bit, right? Let's just go to yeah, the accuracy score. Okay, and I can do y test and y predict. The one in my code, I actually show you how to do it manually. But I guess nowadays I just use this accuracy score just to get things done in a more concise manner. Okay, and I get 1. So that means that my model is actually predicting the same result in y predict and my y test, which is the answer. Okay, so at least you can be pretty confident that your model can perform somewhat, okay in the production, even though this is still biased evaluation. I think this is still okay, like good model. If your flower doesn't change anything much, like if your sample size change, like if your sample actually change in the future, then the model is going to perform poorly. Okay. All right, so we already made prediction, but let's see what the model is doing. And this one is possible because we only have to what?
Is it realistic in real life to get the accuracy score of 1?
It's probably not realistic, okay? Depending on your use case. The reason that this is 1 is that if you go to my scatter plot, right here, you can kind of see that, I mean, you have to take my word for it, but this is group 1, this is group 0, this is group 1, or vice versa, I don't remember. But the thing is that the two classes are linearly separable. So when things are linearly separable, it means that you can get perfect prediction. Because if you are drawing a line like this, then this one is 1, this one is 0. It's perfect. But in real life, you're going to have contamination, meaning that this is 1, but it might have 0 in here. And if that's the case, your model will never give you 100% accuracy because your data is not linearly separable. So that's the reason behind it. Okay, you'll see in the visualization that I'm going to show you. Okay, so I'm going to do. Okay, I'm going to just use my this DS right here, plot DS, it's coming from my utility folder. So this is the reason why you need to execute this block at the first place. But I'm going to use this function to do some visualization. Okay, so I'm going to do plot DS. Okay, plot DS. I'm going to have to put X train, standardize, X test, standardize, Y train, Y test, and ppn. So this function I wrote by myself, and then I just need a lot of things. That's why. There's nothing special about this function. Okay, and as you can see, there are data that are separate to two groups, right? and there are actually no contamination between the groups. So that means that if you were to draw the line like this, so this line is actually coming from the weights and intercept of the model that you just learned, okay? And this line can separate the two groups perfectly, right? This is the training data, this is the test data. So that's why the accuracy is 1. But in real life, you're never gonna get this data, I'm pretty sure. It's gonna be a lot of things in between, and the color is probably gonna get mixed, and in that case, the linear model will be insufficient. You gotta do non-linear model, and that's what we're gonna go talk about a more complex model later on. So there are ways that you can get high accuracy using non-linear model. But right now, this is very easy data. Okay? Yeah, so I'm just skipping down to this line. So this line, this is function that I wrote by myself, and it's, if you wanna see what it is, go into util in the S00, and the plot ds is right here. Right here. Right here. So yeah, it's nothing. It's using Matplotlib basically, the one that I showed you very briefly last time. That's it. Okay. Yeah, and then this one just tells you the what's it called, the decision surface. Okay. So you can think about this. If you have a new data, and then it falls into here, the model is going to predict class 0. So this color is called decision surface. If your new data come in and it falls here, it's going to give you class 1. So that's how the model actually predict new data. Like that's exactly what ChatGPT is doing. Like ChatGPT also have decision surface for the things that you type, and then it's going to say, where is it fall? And then it's going to give you, well, I guess, to be fair, the ChatGPT doesn't give you class, right? It gives you the text. So it actually gives you number, and that number is actually the regression model. So it's not classification per se in ChatGPT. It's more like regressions plus the encoder, decoder thing. So it's much more complex than this one. But the general rule is the same. You gotta have some decision surface to decide of something, and then it's gonna give you that prediction. Okay, so let's do just that. So right now we have finished number 8, right? We have evaluate the model right here, right? And if you are not satisfied with your accuracy, you have to go back to number 6 again. So remember, we can choose the learning rate, right? We can change an eternal change, and why don't you do that, right? Why don't you go back and change your model and rerun, see if your results change or not? Shall we do that? Okay. Let's practice a little bit, right? So I'm gonna go back into my code, and then maybe we can change things a bit. I can go back here and I can start changing the model. So right now the model is too good. Let's make it bad, shall we? So I don't know the value, but you can change into something else. And let's see what happened to the model if you keep changing this value, shall we? Usually the things that affects the model the most is the learning rate. It's eta. So I'm going to try running it again and see if it changed anything. It doesn't. Okay, let me just increase it even more. So 10 is still okay. So I'm going to do 100. So usually you can just rerun the whole thing because it doesn't take that long. Just run all. Just do 100. Does it work? Still good. Okay, let's do 1,000. At some point, I have to break something, I think. Still good. Okay, let's do 10,000. Okay, I'm not breaking it anymore. Let's do a really, really high number. Yeah, I think I broke the model. Yeah, I broke the model. Wait, still the same. Yeah, see the results here? Even though your model can kind of predict the same result, but look at the weights, right? The weights is just blow up a lot, right? See this? My weight is actually this number times 10 to the 12. So your weight is very, very high. So this model is actually too flaky. Like if you change your input a little bit, then you can throw off the prediction very, very fast because your weight is too large. So that's something to keep in mind, that if you want to go into more details, there is a difference between the model that has weights that are 10 to the 12 and weights that are maybe like just 0.1. Actually, the model with lower weights is generally more, it's generally more robust to the noise than the model with higher weights like this. And that's coming from the fact that I just blow up my learning rate. It's too much. So I guess the linear model it's quite robust in a sense that it can still be trained, but for other models, it's probably going to blow it up. Like it's going to give you NaN, which is not a number. So sometimes it just blows up like that. We'll see later on. Okay, so that means that this one probably not a good idea. I'm going to go back to 0.01 again. Okay, just make sure that my weight is not too large. So this one, yeah, something like this looks much better. Okay. Okay, so let's do number 9, right? After you're done with your model training, we're going to predict something. And then when you want to predict something, you usually you need some new data, the data that model never seen. And since I don't have that data, I'm going to create it from scratch. And the way that I do is written in my code right here. Okay, so make prediction, I'm going to use the unlabeled data. So that means that this one, I do not know the answer. And I do not know whether the model will give you the right answer or not. I just need to know the answer. Okay, so let's do just that. So this statement gives you basically just telling you what is the minimum and maximum value for your existing data. So with this, I can see that my x1 min is 1, right? And x1 max is 5.1. So basically, I just want to get the range of the existing data so that I don't use the data that is outside the domain. That's what this statement is doing. And then I'm going to create a new Panda data frame that contains the randomly generated value between those ranges. Okay, right here. So this one, I'm just generating the new x within the same range that I calculate from my existing data. I think I generate 50 of them. You can increase this number so that you have more flowers. So this is the number of flowers that we're going to test. Okay, and the way that we can, and then we're going to do the box plot of it like that. Okay, so as you can kind of remember, like these are the ranges that occur in our data, the raw data. Okay, and then I can even do scatter plot, which you can see that now it's kind of randomly distributed among x1 and x2. Okay, and some of this will be class 1, some of this will be class 2. Okay, and then I'm going to do okay, so I'm going to do this one, right? I have x. Okay, where I have x new somewhere. Where's my x new? Oh, x new is in here. Okay, so right now I have x new, and then I want to find the prediction for my x new. So my x new is a new randomly generated value, right? So in order to do that, you have to go through the same pipeline as the one with the training data. So first, I have to transform my data because this one is still not standardized. So I need to make it, like the mean equal to 0, and standard deviation equal to 1, right? So sc.transform, right? So sc is a standard scalar. So we're reusing the same process that we use when we train the data, right? When we process the training data. So this is x new, okay? And this one is going to go to x new std. Okay. Okay. But once we transform our data, once we standardize our data, we no longer need to train our model because we already have the model. So we skip that and then we go, let me just show you. So remember we kind of prepare the data, right? We do number 3, transformation, and then we skip to number 9. So the prediction part is much shorter. You just get the data, prepare it, and then straight to number 9. So make prediction. So in order to do that, we're going to do ppn dot predict, okay? And then just input the new x into it, okay? And there you go, okay? So that is the prediction of the unseen data, unlabeled data. Okay, and we don't know if this is correct or not, right? Because essentially, if you want to predict something, that means you don't know the answer, but you have some estimation of its accuracy from your training process, which is 1. So I guess assuming that nothing changed in your distribution of flowers, or like the flower, like nothing changed in the flower itself, you should expect this to be all correct. Yeah, that's the best thing that you can say, okay? And I can visualize this one too by putting this into, I guess, into y new, right? And then I can plot it, okay? So let me just show you the new plot, okay? Yeah, so that's what it is. So these are the training data, yeah, so these are the test data that we just create. So again, because we are sampling from the existing distribution, so it's separated into 2 groups very nicely. Okay, and that's the model, I guess the model decision surface. Okay. And there you go, your complete process of doing the training, building the model, and then also doing the prediction, right? I think today maybe before we go, I'd like to tell you more about the actual updates of the data. Yeah, this one's gonna take some time, so let's save it for next time then. All right, okay. All right. So today, I guess that's it. Thank you for coming. See you next time. Yeah.